Hello and welcome to Essential Chemistry for Biology, and we will be talking about basically the chemistry that you need to know. We will be covering elements, bonding, chemical reactions, properties of water, and then lastly acids and bases, and a little bit about kind of what they are. In our class, we will be looking at kind of this, what we call emergent properties. As we get smaller and smaller, and as we get bigger and bigger, these kind of new properties occur. And one of the properties that we want to look at is basically the properties of the chemicals and the properties of the elements that make up life. And in this short presentation, I'm going to talk a little bit about those types. Matter is basically anything that occupies space and has mass, and so life is made up of matter. The stuff that we see is actually matter. This matter comes in three forms: what we call a solid, a liquid, and a gas. And water is an example of these kind of three physical states that occur. Matter is composed of elements. Elements are substances that cannot be broken down into other substances. There's 92 naturally occurring elements on Earth, and a lot of these occur in life. This is the periodic table of elements, and it kind of shows you all the different elements that there are. Of these elements that we're looking at, basically there's about 25 that are really essential to life, and that is, so if some of these are missing, then life cannot occur. So life needs to get these from somewhere. Now, the vast majority of elements that life needs is oxygen, carbon, hydrogen, and nitrogen. And so these would make up the majority of what is required by living things. And again, if we look at a body here and we look at the percentages, most of the body is oxygen by weight. We have carbon, and we have hydrogen and nitrogen, and these together make up about 96% of the body mass. The other 4%, for the most part, are made up of calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. Those are needed in a fair, reasonable number of amounts. And then lastly, we have what are called trace amounts, that each of these is required in less than 0.01% of our body mass, and so we don't need a lot of those. And a lot of times we get these just due to contaminants in the foods and the water that we drink. Again, they're very important because, again, we don't tend to see this. This is a goiter. This is due to iodine deficiencies. And again, without these substances, we wouldn't be in a lot of trouble. Now, when we combine these elements together, we get what we call a compound, which is two or more elements in basically a fixed ratio. The proportions are pretty stable. And so this would include things like sodium chloride, which is table salt, water, H2O, etc. Again, the smallest kind of atom that we have is kind of what we call an atom, and we're not going to get into what an atom is. You hopefully know that atoms are made of protons, neutrons, and electrons. The proton has a positive charge, the electron has a negative charge. They're equal and opposite. A lot of the chemistry of these things depends on how many protons are present, and that's basically about what we're going to get. The number of protons is what we call the atomic number. An atom's mass number is the sum of the number of protons plus neutrons. Again, the electrons don't matter that much because they don't weigh very much. An isotope is an alternate mass forms of an element, and so that, again, in order to be a specific element, it has to have the proper number of protons, but it can have more neutrons or less neutrons. It can have an effect on this, and we're not going to talk about that much, except that these are used for radioactive isotopes, which is can be used in dating. That is how long an organism has been dead or how long has it been around, and also as use as a kind of a tracer to see kind of where things go. Radioactivity can have a big effect on us, and again, the Chernobyl nuclear accident, the accidents in Japan, etc., recently are all things that can have an effect on us. The Department of Energy, which is responsible for our nuclear energy, was actually responsible for funding the sequencing of the human genome so that we could see what this difference is. Electrons are very important because they give us the chemical properties of the atoms. It's the chemical shell on the outer surface that basically gives the properties of that. And so next that we want to talk about, and what depends on these electron shells, is this thing called kind of chemical bonding. We have roughly 3 types of chemical bonds. Ionic bonds, which are formed by oppositely charged ions. Sodium chloride is an example of an ionic bond. The sodium tends to lose its electron and then hence be a positively charged. The chlorine tends to gain an electron and hence be negatively charged. There's a very strong attraction between the positively charged sodium and the negatively charged chlorine, so much so that you have to heat it up to thousands of degrees in order to separate these particular molecules. A covalent bond is formed when basically the electrons in the outer shell are shared. And we have hydrogen, oxygen, and methane are all examples where they share this. Polarity is where basically one part, an atom, tends to share a little bit more than the others. And again, this is not necessarily to scale because the oxygen in reality is many times larger than the hydrogen. And so what happens is as these electrons are kind of shooting around here and being shared by these guys here, the electrons spend a little bit more time around the oxygen because basically the oxygen's a little bit bigger and it takes the electron a little bit longer to move around the oxygen. That presence of the electron gives this oxygen a slight negative charge. The absence of the electron gives these hydrogen a slight positive charge, and what happens is the molecule becomes sticky. The hydrogens, which are positively charged, will bind to the oxygens, which are partially negative charged, and this is what we call a hydrogen bond. If I pull on this molecule here, it's going to pull on all the other molecules because they're attached by these bonds. You are sum total of your chemical reactions, and this is what we call our metabolism. The reactants are the starting materials, the products are the end materials that we've been. Again, remember that chemical reactions can rearrange matter, but they cannot create or destroy matter. Water is very critical for living things. And again, one of the reasons why the Earth is so habitable is because of the amount of water that we have here. And again, that water floats. That water is kind of beautiful. Some of the life-supporting properties of water are that the water molecules stick together. Water has a strong resistance to change in temperature. As we can see, because we live in the bay here, water floats, and water is the common solvent to life. And so the sticking together of water is what we call cohesion. Cohesion is very important because when we pull on this water molecule here, it's going to pull the other water molecule up. So what happens is when water is evaporating from the leaves, it actually is pulling water up through these microscopic tubes called the xylem inside of a plant. And again, in something like a redwood tree, that can be a very, very long distance. Again, the cohesion also gives us a surface tension on these particular molecules. Water molecules can actually form very large heat sinks. The reason is because you can't, unlike a piece of metal or, if you've ever noticed that you can have on a solid surface, that one part of the solid surface can be very hot and another part can be relatively cool because the heat doesn't transfer very rapidly. Water transfers the heat very, very rapidly, and so we tend to see the water goes in there. Again, we can have water cooling, and so as water evaporates, that phase change requires a lot of heat, and that takes heat away from it. So it's one of the reasons why we cool ourselves off by kind of sweating. There's also a significance in that water floats, and this is very critical. When water is a solid, it actually has a lot more airspace. Sorry, I shouldn't call it airspace. Space in between the molecules than it does when it's a liquid. So this means the ice form of water is actually less dense than the liquid form of water. So liquid ice, so the solid ice floats, forming an insulative layer on top of the water, preventing the lower portions of the water from actually freezing. And that's very critical because then, again, if the Earth was a solid ball of ice, nothing would live here. Another 2 words that we really need to know about is what we call a solvent and a solute. When you drink your coffee, when you put your sugar in the coffee in the morning, the coffee is the solvent and the solute is the sugar. Now again, this has some properties on things like sodium chloride, which I told you before was a very strong ionic bond. However, we take that ionic bond and we put these very weak hydrogen bonds on it. We can break this apart. And so even though sodium chloride, you need to blast it with a lot of heat in order to break that bonds, a couple of drops of water will totally disassociate and take that molecule apart. The last thing that we want to talk about is bases. And for the most part, what we're going to talk about at bases, an acid is something that will give up a hydrogen ion, and a base is something that actually absorbs a hydrogen ion. Both of these are caustic substances. And so if we take a look at it, bleach is very basic. And things like gastric juice or battery acid, hydrogen chloride, is very acidic. These are very reactive solutions because, again, hydrogen ions are being released, hydrogen ions are being taken up, and it's very caustic. Again, seawater and human blood have a pH of between 7 and 8, and they are what we call a neutral pH. Life can only occur, at least our life for us, can only occur at these neutral pHs. And so that's basically about it that I'll talk about this particular item. Thanks a lot for learning a little bit of chemistry with me. We will talk about it a little bit more in class.